Okay, so we've kind of played around with the program and things like that, and the goal again is to add a second resistor to this circuit, and we have everything that we need, but we have to figure out what is the current through that resistor is supposed to be. So the first thing we should do is we should just draw the circuit.
Yeah.
That never hurts. I heard somebody say that if you look at experts like Nobel Prize winners, they're always drawing things. So you're halfway to a Nobel Prize if you're going to draw something like that.
So our battery,
Uh-huh.
our capacitor,
Uh-huh.
we have the... Oh wait, no, the resistor's on top.
Well, the resistor, and you're thinking of the RLC ones. That was actually
yeah.
that was just
Okay.
fine. That was just fine. Got a resistor there, so that's R1, and then there's a kind of a switch there, and another resistor in that part of the circuit. And the thing we're really concerned with now is not so much what happens with if the switch is to the right, but really we want to know what's the current through the resistor if the switch is to the left, because we're trying to figure out like how quickly that capacitor is charging up, things like that. And so there's a couple different ways that we could do this. There's the way that I do it, which is to say that is to think about the voltage drop across the resistor. Another way to do it is Kirchhoff's loops. So if you're out there and you know how to do Kirchhoff's loops, that's another way. So maybe we can do that just to show how to do that. Okay, so we got the circuit drawn. Looks good. Here's a question. So if the switch is flipped to the left, is this resistor doing anything?
No, it doesn't make a complete circuit or anything.
Right. So is there any way that this resistor can affect any of this stuff over here?
No.
No. So let's go ahead and redraw the circuit.
Just isolating the relevant parts.
Like I said, Nobel Prize winners do this all the time. This will help us think about it, right? Okay. And so so that's great. So there's no reason why we couldn't put the resistor instead of up there to be right there. That's
Slide
fine.
it over.
It's still connected in the same way to the circuit. And the reason I like having that drawn that way is maybe you could step aside because your shirt is red and the thing's pink. Okay. So let's think about this for a second. So there's the voltage of the battery there. So this circuit, there's a couple different ways to do the circuit, but I like drawing it this way because it suggests that the voltage drop across the battery, it suggests that the voltage drop across the resistor plus the voltage drop across the capacitor is equal to the voltage drop across the battery. So you can write that this way. So V battery. This is kind of how I like to do circuit problems. So it's a little simpler than Kirchhoff's loops, if you guys have heard of Kirchhoff's loops. But so the voltage drop across the battery equals the voltage drop across the resistor. Okay, so that's what that is. Plus the voltage drop across the capacitor. Okay. Now, Blythe, do you remember what the voltage drop across the capacitor is? So this is 10, the voltage drop across the battery. We'll just keep that there. Plus, do you remember what this is in terms of the charge and the capacitance?
That should be Q over C.
Q over C, very good. Q over C, and then what is the voltage drop across the resistor?
That would just be our normal IR.
Right.
IR2.
Okay. And what is it that we need to solve for our program? Do you remember the question marks?
Yeah, we were trying to update this variable.
Okay. So we want to try to solve for this. Now in our program, I think we actually leave it this variable like that, the voltage of the capacitor. And so what I'll do is maybe instead of Q over C, I'll just erase that real quick, and I'll just sort of leave this as V capacitor. And so what I can do is I can subtract V capacitor from both sides. So V cap, right? And then that leaves me with V battery minus V cap equals IR. And then I can divide both sides by R to get the current, right? So divide by R, and then I get this is V battery minus V cap. Now, a fun thing we can do with this result, and by the way, is this R1 or R2?
That's our R2.
R2, so R2 there. So a fun thing with this is that what if the capacitor wasn't there? Thank you. If the capacitor wasn't there, what would the current be through the resistor?
That would just be our typical V battery over R2.
Right. So does that make sense? If this thing wasn't there, you would just get a current of V battery over R2? I think that's pretty reasonable. So it's always good to check your answers to make sure that it makes some good sense. So let's go ahead and put this into the code and see if this is going to work. If it's going to do something realistic for us. Another quick question here. So what happens after a long time?
So the
So what's happening to the capacitor? What's happening to the capacitor as the current flows through the circuit?
So the charge stored on the capacitor increases until this C cap will equal, or the V cap will equal the V battery.
That's right. So initially the charge is 0, so the charge is like a function of time here. And so initially this is 0, but over time it gets larger and larger and larger until the point where this voltage is equal to that of the battery, and then the current will go to 0 after a long time. So that's kind of what you might expect to happen. So so let's put it in the code and see what we get.